Great. So this time we're going to be talking about text classification. We're not just going to be talking about text classification though, because text classification's rather elementary for people who've done NLP before. So I'm going to try to intersperse text classification with also a couple other interesting issues. So there will be some basic stuff and some more advanced stuff or methodological stuff. So hopefully there will be a little bit for everyone. And okay, so let's get started. And as always, if you have any questions, please feel free to type up and ask in the classroom or ask on chat in Zoom. Cool. So this is a slide I presented last time on kind of a general framework for describing NLP systems where we have an input and an output. And we can describe various types of NLP methods this way. And this time we're going to be talking in particular about text classification, where text classification takes in a text and outputs a label of some type. And in contrast to what we did last time, where we tried to design some rules to better understand our data, this time we are going to look into machine learning-based methods, although rather elementary machine learning-based methods. So as a reminder, what this looks like basically is we have a learning algorithm, and this learning algorithm outputs a learned feature extractor and scoring function, W. This time we're mainly going to be focusing on learning the scoring function, W, as opposed to the feature extractor. And we're going to be moving into the learning the feature extractor part in the next class. And then we apply this inference algorithm to learn the test set or dataset. So for text classification, this is basically taking in sentences or documents or any variety of text and assigning it a label. So it's a very kind of broad class of things that we can be doing. And of course, the details of exactly what type of classification problem you're solving are going to make a very big difference in how you need to create data or what sorts of things are important in order to make it work well. This is an example that we gave last time, sentiment analysis. It's just one example, and I'm going to be talking about a few other examples later as well. And this time I'm going to talk about two different varieties of models. I'm going to be talking about generative models and discriminative models. These are important varieties of models for all different types of tasks, not just text classification tasks. So I think it's worth knowing about them very upfront, and then we can go back to them later and find more examples of this throughout the class. So a generative model is essentially a model that calculates a probability of the input data itself of any variety. So if we have an input sentence, X, we can calculate the probability of the input sentence X on its own. Does anyone have an example of a model that's like this? Yeah. A Gaussian, yeah, a Gaussian could model like vector data. With respect to language, any ideas? Language model, yeah. It's not very descriptive, but it is correct, yes. Topic model would be another good example. A topic model, actually, you could also consider it the next variety of model that I'm going to talk about, which is a joint model. And the joint model is where you have the probability of the input data X. So this is the actual observable data that you can see. And then also the probability of some other value Y, where Y is something that you can't immediately observe from the data. I already got a topic model on the Zoom chat, and a topic model is basically a model that infers some latent topics with respect to the input data. So here, X would be the actual sentences that you're seeing, and Y would be the topics that you're inferring. It could also be that Y is the label of your text classification task. And I'm going to talk about exactly how we realize that in a second. Then we have discriminative models. These are models that calculate the probability of a latent trait given the data. So we have this conditional probability P of Y given X. And these are kind of the standard text classification models that we use most of the time nowadays in machine learning. So if we look at an application to text classification, basically what generative text classification does is it learns a model of the joint probability of the text and the label of the text, and then it tries to find the label that maximizes this joint probability. Whereas a discriminative model learns a model of the conditional probability of the label Y given X and finds a label that maximizes this. And so this has a little bit of a, the difference isn't super large in the equations, but the actual way you implement it can be pretty significantly different. Okay, so let's go into generative text classification. So generative text classification is, modeling this joint probability. But before we get into this, I'd like to talk a little bit about language modeling. And I say only a little bit because we're going to talk about it more in the future class. But language modeling essentially is calculating the probability of a sentence. So we have the probability X of a sentence or a text. And the way we calculate this frequently is we calculate the probability of the next word given the previous words. And this decomposition, so we have the next word given the context. This decomposition of the probability of the whole sentence as the sequence or the product of conditional probabilities like this is basically a basic rule of probability. It's not even an approximation. We can just say that this is, a strict equivalence. However, despite the fact that this is a strict equivalence, if we actually want to learn a model that predicts this probability, that's actually pretty hard. And that's, what all of the, companies are spending $5 million training GPT-3 to do. So, this is a non-trivial problem. For the purpose of this class, we will not be spending $5 million to train a large language model. We'll be doing something a lot simpler. So the simplest language model is a count-based unigram model. And as I said, we'll cover more complicated things later. So we'll pick a very, very simple one that makes an independence assumption. So in other words, it makes an assumption that every single word in the sentence is independent of all of the other words. So if we have, for example, the word the is the probability of the word the is about 0.05, which I think is right in a lot of English text or close to right in a lot of English text. Then the probability of the is equal to this, regardless of the context it appears in. So like the is perfectly okay according to this model, despite the fact that it's not actually good English most of the time. And so then how do we calculate this probability? We can do that in a really simple way. We basically count up all the times a particular word appears in a training corpus, and we divide by the total number of words in the training corpus. So if the way we would calculate this is we have 1 million words in our training corpus, we would count up all the thes. See what I did there?
I was hoping to do it.
Yeah. We count up all the thes in the training corpus, and we get 50,000. We have 50,000 of them, so we get a probability of 0.05. Okay, and then we have handling unknown words. So this is an important thing that we need to do in any model that we're going to create of language, because our training corpora are not infinite. So if a word doesn't exist in the training data, this probability that we calculate becomes 0 because, of course, the numerator is 0. So what we can do instead is we can create a distribution that assigns some probability to all words. So how can we do this? Any ideas? Yeah. Okay, and how would you create that prior probability over all of the words? Give an equal probability. Okay. And so how many words are there in English?
Many.
Many? That's good. So I'll just divide one by many, and we'll see what probability we. Yeah, no, this is a good point. It's a hard question. So maybe a kind of correct way of doing this is character or subword based models. You could calculate the probability of the word based on its spelling. So you might calculate the probability of T, the probability of H, the probability of E, multiply them all together, and you get the probability of the. This is a little bit more complicated. So the alternative is to do exactly what you just said. It's a good point. Is we could approximate something like this by assuming a fixed size vocabulary and defining the probability to be 1 divided by this fixed size vocabulary. The problem with this is actually there isn't a fixed vocabulary in English. We can create new words all the time. You know, pick your favorite startup company or like any other like new word that enters the English language. And but anyway, like if we just assume, hey, there's 1 million words in English, we'll set n vocab to be 1 million and divide by that. Okay. So then what we do is we combine the two probabilities with a coefficient. We can call this lambda unc. And this basically gives us the probability of any word. So if it exists in our vocabulary, probably it will get most of its probability from the maximum likelihood estimation part. If it doesn't exist in the vocabulary, it'll still get a little bit of probability from the unknown word part. So that covers all of our bases. Okay. So this is a pretty straightforward way to create you know, probabilities. We don't even need to do any complicated things other than counting up words. So the next thing that we can do is we can parameterize this in log space. And what I mean by this is instead of like multiplying all of these probabilities together, we calculate the log probability by adding them together. And this is also a mathematical equivalence. So why would we want to do this? Why would we prefer to do the right rather than the left? Yes? Yeah, exactly. So it simplifies some things and it also prevents underflow because let's say we have 5,000 words in a document. We start multiplying 0.5 or smaller numbers like 0.001 5,000 times. And very soon we run out of, you know, like floating point in like a 32-bit float. So basically what the log does is it makes sure that instead of becoming a very, very small number like 10 to the minus 50 or something like that, it will become a reasonably sized number like minus 50 or minus 100 or something like this. Great. Okay, there we go. I was worried my my computer had frozen. Okay. So yes, and then once we do this, we can define these parameters as theta xi. And so basically this is an individual scalar parameter denoting the log probability of a single word. So now we have created a language model. We'll create better language models later. But we know how to calculate the probability of a sentence. Now, how do we turn this into a text classifier? Actually, the answer is relatively simple, again. So the joint probability can be based on the following decomposition. The probability on the left is, as you remember, what we need for a generative text classifier. We can split this into the probability on the right, which is a class conditional language model. And the way you can create a class conditional language model, you can do it different ways, but the easiest way is just to train a language model only on the data for that particular class. So like, let's say we had positive reviews, negative reviews, and neutral reviews, just to take the example from last time. We would train one unigram language model on the positive reviews, one on the negative reviews, and one on the neutral reviews. And we would have a language model probability for each of these classes by running these 3 language models. Another thing is, the other thing on the right is the class prior probability. So this, basically what we do is we count up the number of times we have observed this class and divide by the total number of training instances in the training corpus. And if you remember, last time we talked about a bias when we were creating the text classifier. This is essentially a bias. This tells us how likely it is to have a particular class show up in our corpus. So one interesting thing is if we think about this from the point of view of the text classifier or the bag of words text classifier that we talked about before, we can actually express it in this way. So we want to calculate the log probability of a sentence, which is the sum of the log probabilities of each of the words in the sentence. And we want to calculate add it together with the log probability of this class prior probability. And so what this looks like is we can take in each word in the sentence, look up a one-hot vector, in other words, a vector where this is 1 and all of the other ones are 0, where this is 0 all the way up to here, which is 1. And then we take the dot product with the probability of I given the class, the probability of this given the class, probability of movie given the class, etc. And we get a score for this class. And this is also called the naive Bayes classifier more generally, if these feature vectors are not just feature vectors over words, but they could be feature vectors over basically anything else. So the bag of words classifier is where these feature vectors correspond to words. The naive Bayes classifier is a more broad concept here. But basically, part of the reason why I wanted to show this is because the naive Bayes classifier is, or the bag of words based naive Bayes classifier is one way of learning a weight vector that corresponds to these words over here. And there are other ways to learn this weight vector, namely a discriminative text classification, where we learn the weight vector directly. But the point here is that a generative classifier, just count-based addition, is one way to learn the weights that you might use in this. One thing that I should point out is I gave an example of using a very simple unigram model as this class conditional language model. There's absolutely no restriction that you have to do this. You could have a much more complicated language model that learns this probability. You could have GPT-3 calculating this probability, or whatever your favorite, like, strongest language model you have in the moment. So the idea of generative text classification is not equal to the idea of, naive Bayes classifier or something like that. Are there any questions so far about this? Yes. Mhm.
When you are calculating the probability based on vocabulary, I mean, you're setting a vocabulary, and also like you have a lambda to add to probability.
Mhm.
So just one point, shouldn't there also be a normalization on the probability?
Oh, a really good question. First meta comment. I'm sorry, I just realized I don't have slide numbers, which is really bad. So I will add slide numbers to the slide. I apologize for that. So then going back to the actual question was, don't we need a normalizing term because we are interpolating these two probabilities with a lambda? And the answer is actually not. The reason why you don't need it is because we're interpolating two probabilities, like not log probabilities or not anything else. And these two terms add up to 1. So you see one is 1 minus unc and the other is unc. So basically what this is doing, this is equivalent to basically a probability model where you randomly sample either to generate from here or here, and then generate according to that probability. So this is actually a well-formed probability even without renormalizing. However, if you're doing this in log space or something like that, you definitely do need to renormalize. That's it's the difference between linear interpolation and log linear interpolation. You don't need to renormalize for linear interpolation. Yeah.
Another question about this: is this connected to add one smoothing?
Is this connected to add one smoothing? It is. This is different than add one smoothing. I can tell you what add one smoothing is. For those who are not familiar, add one smoothing is basically you have count of the word plus maybe alpha, and then you have the count where like alpha could be equal to 1 or something. And these are not actually. Wait, let me make sure I'm not getting this right. These are close, but not exactly equivalent, I guess, because here you would be, I guess if you're adding them to all of the things in the vocabulary, if you set alpha equal to lambda divided by n vocab, maybe these are equivalent. Maybe possibly.
There's several kinds of smoothing people use. They're all of them slightly different in their motivation.
Right.
Right. And like which one works best? Is it empirical, I think?
Yeah. So I can go into a bit more detail of this. We might do that in the language modeling section, but basically, there's an interesting connection between doing this and adding a prior probability using something called the Dirichlet distribution, and then updating the parameters based on that. So the prior probability is basically the unknown word model. Add one smoothing sets this to maybe n vocab. So this would be equal to n vocab, and then n vocab would be equal to the size of the vocabulary or something like that in regular add one smoothing. It's also called Laplace smoothing, I guess. But yeah, there's a connection. I'll try to make it more clear on slides next time. Yeah, I had one other question on Zoom. So log sum of the features will not be normalized. Longer sentences will have higher probabilities. Longer sentences will have, according to a language model, will normally have lower probabilities because if you add log probabilities together, log probabilities are always negative, so they get more and more negative as you add more. And yes, that is true. Cool. So I will, so if this is very, if you're interested in a little bit more of this, I can, have too many windows. I realize I didn't put this on the references, but there's a more modern version of this that tells you about the difference between these on on like neural network models. So if you're you know the difference between generative and discriminative models, and you want to read a little bit more deeply, you can take a look at this paper as well.
Might be worth pointing out that Danny is a graduate of our fine institute.
Yeah, Danny is a graduate of LTI as well, but that's not why I picked this paper. I just picked it because it's a good paper. Cool. So now moving to discriminative text classification. So why would we want to use a discriminative classifiers? Generative models are a somewhat roundabout way of creating a model to do text classification. They spend a lot of capacity on modeling the input sentences, and we actually only really care in some classification tasks, we only really care about the probability of the output label. And what discriminative models do is they directly model the probability of the output, which is what we care about. On the other hand, discriminative models don't have an easy count-based decomposition, or another way to put it is they can't easily be trained basically from text itself. And so the bag of words generative model looked a little bit like this, and you can see that all of these probabilities can be at least approximated by just calculating counts, right? However, if you tried to do the same thing, what you would need to do is you need to calculate the count of y given x, and there's no way to make kind of independence assumptions like each word in the input is generated independently to calculate this probability in a kind of more decomposed way. So because of this, we have to rely on other methods. Most of the models that I'm going to talk about in this class are discriminative models, and most of them are trained in a very similar way. So this will apply to most of the models that we talk about for the rest of the semester. So what we do instead is we define a model that calculates a probability directly based on parameters theta. And it looks a little bit like this. Then we define a loss function that is lower if the model is better. There are lots of different loss functions that we could define, but the most common one is negative log likelihood. I have a typo there, sorry. I made these slides kind of late at night. But this should be the probability of y given x. It should be this probability up here. And then we optimize the parameters directly to minimize the loss. So once we have this loss function defined, we try to find the parameters that minimize the loss. So if we think of a bag of words discriminative model, let's think about binary classification at first, because it's a little bit simpler to write down in formulas. But basically, let's say we have a positive negative classification. And what we do is we define the score of a sentence as being the score of the class. So this is our bias that we talked about before. And then we have we have a parameter for the bias, and then we have a parameter for the label itself, given each word in the sentence. So one thing that's kind of interesting is this looks very, very similar to the naive Bayes classifier, right? For the naive Bayes classifier, we had exactly the same thing. Except this was calculated directly using counts. So theta y would be the log of this, and theta y given xi would be the log of this. So the functional form of the classifier is actually exactly the same between the two. So it just becomes a matter of how we learn these parameters. Do we learn them in a count-based fashion, or do we learn them directly to optimize the label? So then once we have these, we can convert this into a probability. For example, using the sigmoid function. And the sigmoid function is a function that takes this shape, but maybe the more important thing is that it looks like this. If it's 0, we have a 50% probability. If the input to the function is 0, we have a 50% probability of each of the classes. And if it's greater than 0, the probability approaches 1. If it's less than 0, the probability approaches 0. And we can then apply it to multi-class classification, and sigmoid can be used for binary decisions. For multi-class classifications, we calculate the score for each class and use the softmax function. And the softmax function looks a little bit like this. So we basically exponentiate the score and renormalize so the scores become between 0 and 1. And so all of the scores add up to 1. And the reason why we do this is just because we need a probability. So we basically need to be going from arbitrary scores to something on the probability simplex. And the definition of the probability simplex, what are the two conditions of this? Any ideas? What is the definition of a probability simplex, or of a probability distribution? Yeah.
Add up to 1.
Has to add up to 1. Yeah, that's one condition. And
all of them individually should be between 0 to 1.
All of them should be between 0 to 1. You're right. So the softmax allows you to do that because it makes all of the values positive because the exponent is always positive, and then it normalizes them so that they add up to 1. So everything has to be between 0. So yeah, that's what the softmax does. And then how do we actually optimize the parameters? The parameters are optimized using gradient descent. So we calculate the gradient of the loss function with respect to the parameters. So we have the gradient of the loss function, we have the parameters, and we calculate this gradient. So basically, if we move in this direction, the loss will go up. If we move against this direction, the loss will go down. How do we calculate this gradient? You basically do it using the chain rule. You differentiate back through all of the functions we apply. So we differentiate back through the softmax, back through the sum, etc. We're going to talk about this more in later lectures, so I won't go into the details here. And then we update to move in a direction that decreases the loss. Here, alpha is a learning rate dictating the speed of the movement. So we might move quickly, we might move slowly. So this is standard gradient descent. If you're familiar with neural networks, you're probably familiar with stochastic gradient descent. What's the difference between standard gradient descent and stochastic gradient descent? Any ideas? Yeah.
Standard looks at the whole data at a time, but stochastic looks at little pieces of data. So although the first one might be more accurate, but the second one is a bit faster.
Yes. So I'll repeat that. That's exactly right. So standard gradient descent looks at the whole data, or it calculates the loss that you want to optimize directly. It calculates the entire loss function that you want to optimize, calculates the gradient of that, and takes a step in that direction. Stochastic looks at little bits of data. Standard gradient descent is more accurate. Stochastic gradient descent can be faster because you don't need to calculate over the whole data set. So why is it called stochastic gradient descent? Why is it called stochastic? Because you choose points randomly. Yes, exactly. So it's a sampling-based approximation of the true function that you want to be sampling, you want to be optimizing. So you subsample some of the data, and that approximates the actual function. For I had one question a while ago that I'd like to get back to. So why are we going to focus on discriminative as opposed to generative models in this class? That's actually a really good question. It's not that we're not going to cover generative models at all. It's just that discriminative models are currently much more common in the NLP literature, and because of that, we're going to cover them more. I like generative models, so I want to cover generative models some. So we'll definitely cover them to some extent. Great. So one thing to note is that this is first order gradient descent. There's also methods that allow you to do consider second order information like Newton's method and LBFGS. I'm not going to go into the details of these, but the basic idea is that instead of just considering the direction the function is moving in, it's also considering that the function is curving in a certain way, and this allows you to more effectively adjust like your learning rate or your direction of movement, etc. For simple models like bag of words models, it's feasible to calculate things like Newton's method and LBFGS. And so it's actually a much better idea to use this if we're going to use like scikit-learn or something like this, like we're going to do in the code example. You will be using something like these methods. For things like neural networks, these methods can become very slow. And it's not very common to use full gradient descent. It's more common to use stochastic gradient descent. So we tend to stick with first order methods. Okay. So that's kind of the overview. We have a code example that you can use here of a discriminative text classifier. I can show you in the code repository. It's also linked from the class website. So we have the bag of words classifier. Basically, it's very similar. It looks very similar to the one that we talked about before. But instead of having kind of a rule-based way of extracting features, it extracts basically every word as a feature. It handles things like indexing. It extracts the features from each training example that we would like to use. It has an example of classifying over some sample data. And then it defines a logistic regression model from scikit-learn. So we're not creating this from scratch, but using an existing scikit-learn implementation, and fits the model and tests it. So if you want to take a look at that, you can. Cool. Okay. So now I'm going to get into some other things, and from here on, I'm going to talk about kind of procedural things that are really, really important to know, regardless of the type of NLP experiment you're doing. I'm going to use text classification as an example, but I'm not going to, but they're definitely not limited to this. So for evaluation, we're going to, very often what we want to do is we want to do model comparison. So we have one model, we have another model, we want to know which one we should be using, or whether a change that we've made to a model is making an improvement. So how do we tell which one is better? The standard way is basically train both on the same training set, evaluate on a development set or test set, and compare scores. Basically, whichever one has a higher score is the one that we think is better. The funny thing is, this sounds really basic, but like actually in NLP, even this really basic procedure isn't done all of the time. Like sometimes people will train on different training sets and evaluate and say one model is better than the other. They might say that some like agglomeration of data and model is better than the other, but it's kind of hard to say like which methodology is better than the other. So I think it's really important. What are all the different things between the settings that you're testing? And what you can say is that given one combination of settings, one is better than the other, but it's something to keep in mind. Just to give an example, like a lot of the pre-training papers come up with a new method, but then they also train it on new data, if you're paying attention to that field. Okay, so going back to calculating a score, the simplest one is accuracy. It's basically what percentage of labels do we get correct? So we count up the total number of labels in the dev set or test set and divide the number of correct labels by that. This is very simple, easy to calculate. One issue with it, however, is often we care about a particular class, often a minority class in the data. And just to give an example, like let's say we were doing toxic SNS post detection. Most SNS posts are not toxic. And because of this, but we really care about whether we're able to detect the toxic ones. So let's say only 0.01% of SNS posts are toxic. Or I can make it not percent. Let's say 0.01% are toxic. Maybe I'm too optimistic, but let's say that's the case. If that's the case, then your accuracy by just saying everything is not toxic is going to be 0.9999, which seems really good until you realize that you're not detecting any toxic posts whatsoever. So using precision or recall or F1 measure is really important when like the thing that you care about is very much in the minority. So the way precision works is basically precision is the count of the number of system outputs that you get correct. So for example, if the system says 1,000 posts are toxic and 400 of those are actually toxic, then you would have a precision of 40%. Recall is the precision of human labeled, correct ones correct. So basically, if actually 500 were toxic, then you would have a recall of 80%. Then F1 score or F measure is the harmonic mean of both that tries to balance the two. So up until now, I think a lot of the stuff is, relatively standard. Probably most people here have used them before. One thing that I think we definitely need to do a better job of in natural language processing in general is statistical significance testing. So this is another really important basic skill to have. And the idea is we have, for example, two models with similar accuracies. We might have other, other comparisons we'd like to make as well, but let's say we have two models with similar accuracies. So we have a generative model and a discriminative model across dataset 1, dataset 2, dataset 3. I'm sure you've seen tables like this before where people bold the highest scoring one. But if you look at the first one, is the difference between 85.4 and 85.3 really worth bolding the numbers for? It might just be, if you reran it with a different random seed, you get a different answer. If you reran it with different data, you would get a different answer. So how can we tell whether the differences are due to consistent trends that might hold on other data sets, even data sets that are created using the exact same methodology as the data set that we have here? And the answer is statistical testing or statistical significance testing. I'm only going to cover it very briefly now, but I have a reference here if you'd like to learn more. It's called The Hitchhiker's Guide to Testing Statistical Significance in Natural Language Processing. So you can take a look at that if you'd like. And the basic idea is, given a quantity, we want to test certain values of uncertainty with respect to the quantity. two very common ones are p-value, where p-value is what is the probability that a difference with another quantity is by chance. So this is, if this is lower, there's a larger likelihood of a statistical significant difference between them. So we can say this is actually a real difference that we would expect to see on other data drawn from a similar distribution. Confidence interval is like, what is the range under which we could expect another trial to fall? So if we created another similar data set using the same methodology, what is the range of accuracies that we could expect? Another important concept to know about is unpaired versus paired tests. This is something that, that I think not necessarily everybody would know. And basically an unpaired test could be something like a standard t-test. What this does is this compares means of a quantity on two unrelated groups. So this would be suitable, for example, for trying to test the significance of a difference of accuracies of a model on two data sets. Like, let's say we have one model and we want to test whether its accuracy is different across two different data sets created with a different methodology. An unpaired test would be appropriate for this. To give another commonly used example, let's say you wanted to know whether the height of people from the incoming class of 2021 was different than the height of people from the incoming class of 2020. So these are different people. They're different populations, but they all have a height that we could measure, and we'd want to measure the difference between them. A paired test compares means of a quantity on one data set under two conditions. So an example of this would be testing significance of a difference of accuracies of two models on one data set. And this is very often what we want to do, right? We have a generative classifier, a discriminative classifier. We'd want to test the difference between them on the same data set. Another example would be, let's say we had everybody in the class and we wanted to test whether they sleep more on weekends or weekdays. So there, everybody in the class is still the same, right? It's the same group of people, but we have two conditions. We have how much sleep on weekends and how much sleep on weekdays. So in NLP, it's much more common to be interested in the latter. And there's also good news about this. Paired significance tests are much more likely to yield significant differences because you're controlling for the differences that are based on data set selection, for example. Oops, I broke my animation. So I'll just go there. Okay, so there's many different statistical tests, some of which are in the reference I gave you. There's also a great course called Intermediate Statistics if you want to spend a whole semester learning more about statistics. But my go-to for doing significance tests is a Bootstrap test. And basically, it's a method that can measure p-values, confidence intervals, etc. And the way you do this is by resampling data. And what you do is, like, let's say you have a data set, like a dev set or something like this. You resample many subsets from your dev set or maybe test set with replacement. And you measure accuracies on these many subsets. So, you know, each of these accuracies here in the blue and the red kind of represents inaccuracy on one of the data sets. And this can be used to measure confidence intervals or whether there's a significant difference between two methods. So on the left side, we have the way of calculating confidence intervals. And the way you could do this is you could measure 10,000 times, and then you throw away the lowest ones and the highest ones. And the interval of remaining scores left is your confidence interval. So you might throw away the bottom 250 and the top 250. And then the highest one that you didn't throw away and the lowest one you didn't throw away is your confidence interval. Another thing you can do is, let's say you have two models, you resample the data set 10,000 times and you see how often model 2 beats model 1 and vice versa. And if model 2 beats model 1, 80% of the time, like I have on here, then you can say you would have about 80% confidence that if you had a new data set, you would have about 80% confidence that you would have a new data set, then the one model would win. If you resample 10,000 times and model 1 only wins once, then you would have basically 99.99% confidence that model 2 would win in a new setting. And typically, when we talk about like a significant difference, it's pretty standard to say if P is less than 0.05, this is a significant difference, or P is less than 0.01. This is a significant difference. I personally find these pretty arbitrary, actually. Like, why do we care about 0.05 but not 0.051 or 0.05 or 0.49? But nonetheless, saying that is probably better than nothing. So then the idea would be you do this. If model 2 wins more than 500 times, then you would have more than the chance of model 2 not winning would be less than 5%. So basically, then you could say that was a statistically significant difference with 0.05 probability. And then what you would do here is in your table here, you would only bold things if there was a significant difference. Yeah.
Do we usually throw out the values for confidence? I mean, like comparing the models?
No, you don't throw out the outliers when comparing. That's only for calculating confidence intervals. Yeah.
How would Bootstrap test work for data sets which are very imbalanced? Like say the example you gave, which has like say 99.99% of one class and only 0.01%. And because say one model was only giving one class, so it would win most of the times.
Mm-hmm.
There's a model which is better trained but has a lower accuracy. That would be losing most of the time, but might have better training.
So very good question. Maybe I'll talk about this and then get back to that question. So the advantage of Bootstrap tests is they're very easy to implement. In fact, we have an implementation in the code example, which I'm going to show you now. Another really nice advantage of them is they're applicable to any evaluation measure. And the reason why they're applicable to any evaluation measure is when you're doing this model comparison here, you can calculate any measure you want. You can calculate accuracy, F measure, precision, recall. And in any case, you could still compare the two values, right? You just need to calculate the evaluation measure here. That is not the case for most other statistical tests, like t-tests or things like this, which have some assumptions about the distribution of the values. The disadvantage of Bootstrap tests is that they can be biased on very small data sets. So if you have a very small data set with like 50 examples or something like this, they might not give you robust statistical estimates. Going back to the question, if you have a very imbalanced data set, I don't think imbalance in itself is a problem. I think it would be a problem if the value that you cared, the class that you cared about was so underrepresented, there weren't very many examples of it in the data set. So if you have a very unbalanced data set, but it's very large, that's fine. If you have a very unbalanced data set, but it's small, then you might have issues. But I think actually one of the good things about statistical tests is on large data sets, they tend to get better, like more statistically significant results. On smaller data sets, they tend to not give you statistically significant results. And actually, I think that's fine. That's saying, like, look, if you want a robust result, you need to have a bigger, more reliable data set to test your models on. So yeah.
Would it be more robust if you retrain every time you like change the data set, or that?
Would it be more, oh, if you retrain?
Yeah.
So one thing to note here is that this is taking into account variance due to the sampling of the data. So basically what it's taking into account is if you had a new data set that was sampled in the same way, would you expect to see a similar difference that you saw here? If you have a model that is retrained or not, if you have a model that's retrained using a different random seed, that's a different variety of, you know, like, that's a different variety of variance that you could have. So this is not taking into account variance due to like a random seed or something like this. What you can do is you can do, this is maybe more complicated than I'm going to have time to go into in detail, but you can do things like hierarchical bootstrap tests, which are basically like you first sample a random seed, you run two models using that random seed, and then you sample the difference between them, and you do, now you have a thing where you sample which model do you use, or which random seed do you use? Do you use 0 or 1 or 42? And then you sample a data set and you measure the difference between them. So this is called a hierarchical bootstrap test that allows you to take into account different varieties of variance. So I'm happy to discuss more about this, but it's a kind of a fine point. So good question. I had a couple of questions on Zoom. With bootstrapping, which performance metric is reported in the result table? Is it the average of all trials or interval boundaries? That's a really good question. I would still report the results on the full data set in the result table, because basically this is measuring variance within that full data set, but the full data set is still the most robust. That's still the most robust estimate of the true accuracy. So this would be the accuracy on the full data set. You can also report confidence intervals. I actually sometimes hesitate to report confidence intervals here because a lot of people don't understand that the confidence intervals are telling you how much the models will vary due to data set selection. And so if, for example, you could have a very robust, statistically significant result between the generative and discriminative model on data set 2, but still have their confidence intervals overlap. And the reason why is because there's harder and easier data sets. But regardless of whether the data set is harder or easier, the generative model is always better, for example. And that's actually the reason why paired tests are better at detecting these differences. So paired tests control for data set selection. So I think that's an important thing. And just to reiterate, the way you would do a paired test is when you're making a comparison, this comparison is always done over the same data set, not different data sets. So if it's a hard data set, it will be hard for both models, basically. If bootstrapping is less robust on small data sets, what should be used instead? Very good question also. On small data sets, if you are using a metric like accuracy, you can use a parametric test like the student's t-test or something else like this. There's also a paired test called the Fisher's exact test, which I think is the best possible test you can use for binary classification. If I get that wrong, I apologize, but I think that's correct. And what is a good rule of thumb for a subset size versus number of subsets versus test set size when bootstrapping? That's also a really good question. I think, but I am not very confident in this, that like 1/2 is supposed to be good with respect to the subset size. The number of subsets, the more you have, the better. It's just slower. The more you have, the better an estimate it is of the true value you're trying to predict. Yeah, great questions. So we have an example of the Bootstrap, and it's so simple that you have no excuse for not using it in your projects. So remember when the end of the semester comes around. The way it works is basically like this. You can see that you have the gold output, the system 1 output, the system 2 output. You can get an array of each of them. You get system 1 scores, system 2 scores, and for each of the samples, you sample a subset of the indexes, and when you get the subset of the indexes, you can calculate, here we're just calculating accuracy, we're calculating the average number of things correct. So this part could be replaced by any evaluation metric that you would like. It could be replaced by, F measure or a recall or something like this. But notably, you're calculating it over the subset. You're not calculating it over the full data set. And if the system 1 score is higher than system 2 score, one has wins, like system 1 wins. Otherwise, system 2 wins, and then you also measure ties. And you can print the win statistics and other things like this. And then here is an example of printing the confidence interval. Cool. So for the last part, I would like to go on to dataset creation. This was actually, creating this section was actually interesting and informative for me as well, because I don't do a lot of text classification, so I wasn't super familiar with the datasets. So the task definition, the first step in dataset creation or curation is defining what task you want to be solving. In many cases, you'll need to create a data set yourself. Some cases you can use an existing data set, but still you'll need to curate it into the form that would be useful for text classification. In order to do this, you'll think about what are your classes, create an annotation standard, write down the classes and class definitions. Try annotating yourself and note any hard examples in the class definitions. This is really important. And allow, once you start hiring annotators to help you out, on whatever, you can ask them to share hard examples with you and further refine the standard as you progress. For source data collection, this is also actually quite important. If you randomly pick articles on Wikipedia and then you're going to be processing social media, you're going to be in trouble, right? There's going to be a huge mismatch between them. So when you create source data for whatever data set you would like to be using, you'll want to collect textual data that is appropriate. So like I said, does it match the data you'll be expecting to process at test time? Another thing that's really important is it representative? So if you create a data set that very closely matches what you want to process at test time, but it's, like 80% people of one demographic group, you're going to expect to do a lot worse on people of other demographic groups, and that's not very fair, right? Languages, if you only collect in one language, you're only going to be able to process one language. Also, are you collecting data from a single domain or multiple ones? If you only expect to process a single domain, it's fine to collect from a single domain, but it'd be good to have multiple ones if you want it to be more robust. For annotators, if you're just doing research, I am actually can pretty strongly recommend that you don't go to MTurk right away and you just ask your friends to help you out. Buy them an Amazon gift card or a beverage or something like that. And if it's relatively small scale but high skill, that's going to save you way more time than going out and recruiting people. Another thing that I use some of the time is freelancing sites. So if you have a medium skill task, like let's say you want to have a Python programmer, it's going to be hard to find them on a crowdsourcing site, but you can find them on a freelancing site. Or let's say you want a bilingual speaker. My favorite one is Upwork, but there's other sites as well. And then if you really want large scale and lower scale tasks, you can go to crowdsourcing sites. These can be cheaper and it's easier to find people. We still encourage people to pay a living wage to people on the crowdsourcing sites. So calculate, how much money they would need to make a good living in the place where they are and make sure that you're paying that. Because, we don't want to be exploiting people for pennies an hour. There can be a very big difference in quality. So there's a reason why I recommend your friends. We have an example from this race data set where the second to last line is Turkers and the last line is CMU students on a reading comprehension examination, and Turkers got 69.4 and CMU students got 94.2. So if we want to say human performance, which humans are we talking about? Are we talking about people you're paying several pennies to solve very hard high school level reading comprehension problems, or are you talking about people who are actually motivated to do the job? A similar thing for translation also, there's a very stark difference, even in professional translators, on whether they know that somebody is going to be reading their output and care about it, or if they know they're creating empty training data. And if they're creating empty training data, they're going to be less motivated than, if they know they're going to be seeing their translation output online, basically, and people are actually going to be reading it. What's the gold standard for the race data set? The gold standard for the race data set here is a reading comprehension data set. So the gold standard is the correct answer annotated by the people who created the data originally. So there's also a really nice paper by Bender and Friedman, 2018, on data statements for NLP. I don't think this is the only thing you should be considering, but it has a lot of recommendations that could be useful. And it's a checklist of things to document about your data set in some way. One is curation rationale. Why did you make it in the first place? Another one is language varieties. So what language is it? What dialect is it? Where did the people come from? Speaker demographic, what demographic did people come from, what gender, what ethnic group, etc. Annotator demographic, who annotated the data. So if all of your annotators are graduate students, but all of the people speaking are, 13-year-olds or something like this, your slang might already be stale. I know mine is plenty stale, but your online slang might not be good enough to interpret their, what they are saying, for example.
I just learned the word finsta.
Okay. So
apparently a social media thing.
Yeah. So basically, who's annotating it is also important. Speech situation, where are they? In what situation are they speaking? Text characteristics, what genre is it? Other things like this. Recording quality, if it's a speech or multimodal data set, what equipment was used to record the data? Other notes. So this is kind of a catch-all. There's, of course, a lot more information here.
Exactly, with speech people, they'll specify what mic they're all going to buy. It's they're going to do more than one, because a different mic will make the data too different.
Yeah.
They'll all buy the same brand of microphone.
Yeah, and for speech in multimodal, a different mic might make things very different. A different reverberation setting, so this hall versus something else might make something different. Also, can anyone hear the air conditioner here? Yeah. Did you notice it before I mentioned it? Yeah. So that also makes a difference. So.
Well, actually, even with like commercial TV recordings of things, they'll record 30 seconds of silence in the room, because otherwise, when they edit it, people will notice. You have to use the silence from the room in this first sequence.
Yeah. In case you couldn't hear, commercial TV editors will use the silence in the room to like edit things together, because you'll notice the difference between the silence in the room and the like silence stuff. So yeah, that's a lot of stuff about speech, but you know, I recommend this paper. It's a nice one. So based on this, I kind of went through some text classification data sets. As I said, I don't work on text classification a whole lot, so I'm not an expert here. Maybe if you do, you can go back and look at your favorite text classification data sets and see what the answers are here. For the Stanford Sentiment Tree Bank that we're using, I actually have to admit, I didn't really know the source of the data until I looked it up yesterday. So in addition to standard, so the Stanford Sentiment Tree Bank, in addition to standard tags, it has syntactic phrase tagged with sentiment. The data is reviews from RottenTomatoes.com collected by Peng and Lee in 2004. So these reviews are now 17 years old. And you can imagine that might be a problem if you wanted to build a sentiment classifier for 2021 reviews. Like all of the actor names, not all of them, but many of the actor names are going to be stale, right? For example. So that's a kind of interesting thing that you might like to know about the data set if you're using it for something practical. Annotator details. Basically, the main detail that I saw in the paper was people from MTurk annotated 21,000 sentences. They didn't give any information about quality control. They didn't give any information about like other aspects as well. There's also this AG News dataset, which is used pretty widely in text classification. News articles categorized into 4 classes. The data is from an academic search engine. I couldn't tell exactly when it was gathered, but I guess 2004. Kind of eerie coincidence here. And the curation rationale was as a test bed for data mining in IRs. So they didn't actually have any reason to collect this data other than just to test models. Then there's a DBpedia, also very widely used text classification data set, classification of Wikipedia entry, description, text into 970 or 219 classes. The data is from Wikipedia for sections. It was gathered several years ago. And the curation rationale was as a test bed for text categorizations. So one thing I found kind of interesting was going through these kind of widely used data sets. They were all created to test how well text categorization is working, as opposed to like actually do anything useful, except for the first one. The first one, this, you know, it can be used for detecting the sentiment of other reviews that aren't marked with stars, for example. But yeah, so some interesting things to think about. You know, there are other data sets that did have a curation rationale other than just performance estimation. But yeah. And why is it important to understand the curation rationale? Would that ever affect whether you would actually choose to use the data set? Yeah, that's actually a good question. I think the answer is the moment you start to build anything practical, anything that you really want to work, the data starts to be something you worry about a lot. The quality of the data, the weird, you know, design choices they made in defining their tag set, the coverage of the data with respect to the domains or demographics or whatever that you care about. And so the curation rationale is a proxy for that, because if they created the data set for a different reason than you are, the things that they'll care about are going to be different. So they probably weren't paying as much attention to some of the things that you do care about. So that is pretty important, I think. Is there a central place online to find these NLP data sets? That's a really good question. One thing I didn't mention is on the class website, I think everybody or many people might have noticed this, but on the class website, we have a schedule. And there is, every day, there's a link here. And this, these are the references for today. I found these data sets here in this deep learning based text classification and comprehensive review. This has a list of data sets. I think they didn't cover the things that I covered in the slides here, so I had to actually look in the original papers, but I think it's a good place to start. One thing that I should mention also is there are actually a lot of very good places to get data sets, kind of like central repositories or look at data sets. One is Papers with Code, which has a list of data sets here. And you can go to things like text. You can search and things like this. Another really good resource is Hugging Face datasets. And this is a place where you can get data sets. And one really nice thing about this is they have kind of wrapper code that makes it easy to download them and process them into a standard format. So these would be my two main recommendations as a place to find them. One nice thing about both of these repositories is they have started to make an effort to cover some of the information that I talked about before, like curation. Why were they curated? What demographics do they cover? What language varieties do they cover, et cetera, et cetera. That being said, these are by no means comprehensive. So another good way is just to search Google Scholar and see if anybody has published a data set there. So, cool. Yeah, that's all I have for today. We're at the end of the class. So thanks, everyone. And I'm happy to take any follow-up later.